Hi, everybody. Thanks for coming in here. It's good to see you all. I'm Stephen. It's funny. So I do a lot of presentations. I basically do this for a living instead of having a real job. I used to have a real job. I used to be a systems administrator, Unix admin, email administrator, storage administrator, all that good stuff. Somehow I escaped. There was an escape pod. They were trying to shoot me down, but they didn't. Yeah, I won't stretch the metaphor, but help me. You're my only hope. So people always have like descriptions of who they are, so I thought I would make the most ridiculous description possible of who I am. So there we go. If you get any of these references, I appreciate it. So I'm a guy. I talk about storage a lot. I love storage because really, who doesn't? And one of the things that I wrote about a few years back, actually back in 2010, was what I called the 4 Horsemen of storage. And if you don't like my craptastic art, do your own presentation. So one of the things that I've noticed over the years of studying storage and the development of storage systems is that effectively we can't escape from 4 simple truths about storage. And here they are. I'm going to tell you what the truths are, and then I'm actually going to tell you how to escape, sort of. So let's start with number 1. Number 1 is spindles. Now, you've just heard from Micron that disks are going away. If all of the world's capacity, if all of the world's fabs were converted to making flash memory exclusively, we still couldn't replace a tenth of the disks. Disks aren't going away. You know what else is not going away? Tapes aren't going away, right? We have a whole world of storage options. Now, flash is here, and flash is important, but flash doesn't mean that disks are irrelevant. So let's start with the rule of spindles. Rule number 1, Horseman number 1. You can't escape the nature of disks. They're mechanical, they spin, they heat up, they move around. And what this means is that there are certain limits to what disks can do. Effectively, the thingy has to go around, and the other thingy has to go in and out, and the time that it takes that to happen is a finite amount of time because it's based on physical movement. It's based on physical properties. It's based on physical things. And in order to optimize this kind of performance, there's very little you can do. Now, one of the things you can do is you can focus on where the heads and the platter is instead of where the heads and the platter is not. In other words, sequential access versus random access. So if this is the head right here, this is supposed to, it looks like a tennis racket, but I think it's supposed to be a magnifying glass. If this is the head right here, this tennis racket, and the disk is moving around and around, right? If I need the data that's out here, right, I'm going to have to move the head and I'm going to have to wait for the disk to come around. But if I need the data that's right there, right next to it, I'm in much better shape because I can just get that. In fact, it's basically free to get that because the disk's already spinning and the head's already there. That's why sequential access is so much more important than random access when it comes to disks. Now the problem is this isn't how we use storage. Your applications don't say, oh, hey, I'm going to be super careful about where I put my data so that they're all right next to each other, right on the same disks, right? In fact, in the enterprise, we go the opposite direction. We go way in the opposite direction, and we say, well, we need data protection, and we need RAID, and we need all these other levels of abstraction above this storage, and I'm going to talk about that in a lot more detail. And what this means is that it means that what we do with disks are really bad for disks. What else? Well, how do we get past this? Well, for years, we've been combining spindles. And essentially what that means is that you take some I/O from this one, and 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 you write all of them at the same time, or you read all of them at the same time in order to improve performance. But that doesn't really dramatically improve performance. It improves performance moderately because it means that you can, take advantage of, the I/O operations here and the I/O operations here and here. Just kind of by way of, information, the average disk drive will give you about 100 I/O operations per second in normal use. Maybe it'll get a lot more if you're doing purely sequential access. Maybe it'll get you a lot less if you're doing random, but let's just say 100 for now. If we have a disk set that includes 5 disks, we might be able to get 500 probably reading because you're probably using parity calculations, all these other things. But let's just say, again, good, real world scenario. Let's say we could get 500 IOPS out of that guy. We'd be pretty happy with that. The problem is that's not actually all that fast. The SSD in my Mac here can easily do 50,000 IOPS. This is very, very different, right? This is not just an order of magnitude. This is, what's that, 2 orders of magnitude? 3 orders of magnitude? I don't know. It's a lot. It's a lot of difference. No matter what we do with disks, no matter how wide we spread them, we will never approach the performance of flash or of any other kind of solid-state storage. But we can't get away from disks. We can't just say, okay, well, forget it, no more disks. So what can we do? Well, we can add more spindles. I remember I was sitting in here and listening to Scality. Hi. Their clever solution to the disk question is ridiculously wide. Okay? Imagine, a RAID 5 set. RAID 5, contrary to popular opinion, doesn't mean 5 disks. It means, it's the arrangement of data. But you're probably not going to have more than like 10 disks in a RAID 5 set, even in the most, extreme circumstances. With a truly distributed object store, you could have 10,000 disks all working together, okay? That's incredibly different from, a RAID set and a controller and things like that. It's night and day. So if we add a lot more spindles, we can attack the spindle problem. There's another way to do it, though, and I'm going to talk about that in a second. The real problem with disks is that disks just can't get much faster. You can't make the thing any faster, really, than it is. Now, we could make the disk spin a lot faster, but the problem is there's a limit to how fast it can spin. There have been 20,000 RPM disks, but those were insane, right? 15 was about as much as we ever got in the data center. The problem with a 15,000 RPM disk, though, is that it's really only giving you twice the IOPS, not 10 times the IOPS, right? And that's about as good as we can get. Another thing we can do is we can make the disks smaller. It seems kind of weird that would make it faster, but it does, because what it means is that little guy, that little head, has less room to go back and forth, less room to move. That might help, but when we make the disks smaller, they hold less data. And so it's kind of perverse. When they spin faster, they hold less. When they're smaller, they hold less. So essentially what's happening is kind of the opposite of what you'd think is happening. Disks aren't getting faster, disks are actually getting slower. So 15,000 RPM disks are kind of going away. We're really not looking at those anymore because they really don't provide all that much benefit. The same for those tiny disks. For a while it looked like we were going to go to 3.5, 2.5, 1.8, and have these arrays of like a million of these little spindles all spinning around. But we found a better solution. And the better solution, frankly, is cache. It's right in front of us. And I don't mean the other kind of cache. I mean memory, solid-state cache. The problem with cache is that it costs a lot of cache to get a lot of cache, and it becomes counterintuitive there, because essentially what happens is you can look at it and you can say, oh my gosh, SSD, DRAM, they're super, super fast. I want to go there. That's what I want to put all my data on there. You can't really do that. You have to have a system where you set up tiering. Now, most people use a pyramid, which I think is ridiculous. I'm using a wedding cake because I think it much more adequately reflects what we do with cache. We have a little bit of RAM, we have some more flash, we have some disk, and we make a tiered system. We can take advantage of the performance of flash to overcome some of the limitations of disk. And how this works is pretty simple. Essentially, we write into flash, or actually in most systems we write it to RAM, then we put that into flash, then eventually when we're ready we can put that on disk. What this means is that for most normal use cases, the performance is indistinguishable from the performance as if it was all flash. The problem is this guy is smaller than this guy, and so there comes a time when you overflow your cache. And no matter how much flash you have, we still won't ever have enough, because frankly what we want is an all solid state system. So let's talk about buffers a little bit. Let's geek out a little bit about these things. What can you use disk for? Well, The easiest thing you can use disk for is reading from disk rather than reading, or I'm sorry, reading from flash rather than reading from disk. The reason this is the easiest thing and not the other thing, writing, is that it's actually fairly difficult to make sure that you have, that you're not going to lose data if you write it in one location and then move it to another location. It's much, much easier just to use flash as a read cache. This guy is interesting too. On disk drives, one of the most important uses of RAM is not to accelerate performance, it's to match performance. Because the disk is so much slower than the I/O interface that it's talking to, that if you tried to basically take in, let's say you're using like 3 gigabit SAS or something like that, if you tried to take that 3 gigabits into the disk, you could never do it. And basically what you'd do is you'd have to push back all the way back to the application saying slow down, slow down, slow down. So we need to have somewhere for that data to go at full throttle through that bottleneck that is the hard drive. And I'm going to talk about bottlenecks in a second. Another thing that we can do, we can read around the data. We can prefetch the data. Basically, we can take advantage of the fact that the head is over this section of the disk, and if I read some of that data, I can then maybe have it ready in the future. And I'm going to skip the rest of these because I want to talk about this. Another thing, basically another concept I think that is important to understand when it comes to disks and caching and so on is the difference between write through, write back. So essentially, most systems use a write through cache because, as I was saying a minute ago, we want to make sure that we have consistency. We want to make sure that we don't lose data. Most systems are going to take data from the host, go right to the cache, and then immediately go down to disk. This slows the system down somewhat, and it doesn't relieve the disk of all the I/O load. But the nice thing is that we don't then have to worry about what happens if the cache and the disk gets out of sync. This is less important if you're talking about a single drive, as you can imagine. But it becomes really important when you start building whole solutions, whole storage solutions on this stuff. Because if we think of this instead of just as a chip, as a cache, what if this was a controller, an array controller? What if it was a virtualization system? What if it was something in the hypervisor? Suddenly we start moving back and back and back and back from the disk, and that leaves more and more sections, more and more spots for everything to slow down below it and everything to break below it and for us to lose data. So even though this guy's preferable, that guy's way more common. By the way, I'm going through this fairly quickly because I've only got like half an hour to get through all this stuff, so sorry about that. So what I'm trying to say here, though, is that basically, you know, spindles are annoying. We've got to figure out how to get more I/O. Throw some memory at it. Sounds like a good solution, but it's not a complete solution. There's got to be more to this. Let's say that you had a perfect system, a perfect caching system. It was that wedding cake where you've got RAM and you've got flash and you've got disks, and everything works as you expect. Well, you still have to worry about the I/O band, the I/O in between. And this is another thing that we've had to deal with in storage for many, many years. It's not just disks, and it's not just arrays. There's all sorts of other links in the chain. I/O, in fact, as I say here, most I/O has to go through at least 5 different buses between the CPU and the disk itself. That's 5 different speeds, 5 different command sets, 5 different opportunities for the I/O to be mismatched. Remember I was talking about, you know, the mismatch between channels. And frankly, 5 different places for data to be lost or corrupted. And as I'm going to talk about in a second, it's also 5 more problems, places for there to be problems in terms of understanding of the data. But let's take it this way. Historically, IT has been about bottlenecks. And the history of IT has been about moving bottlenecks around. At least the history of storage has been about that. And if you go back to the very beginning, you know, the first storage systems, tape-based, you know, punch-based, core memory, they were fairly slow. And the systems were basically throttled by the storage. Because in effect, storage and memory were sort of mixed up in those systems. In fact, one of my fun IT moments was going to Bletchley Park and seeing Colossus, one of the first computers. True story. Colossus was clocked not by a clock, but by the storage drive. They actually had a ribbon of tape running through it, and the ribbon of tape actually had little holes with a light that would shine through it, and each time it shined through, all the vacuum tubes would be allowed to click once. And so they could actually, it was variable speeds, so they could actually turn it up and have that tape move faster, and the whole system would go faster. Or they could turn it down and the whole system would go slower. The reason they had to do that is because storage was the ultimate bottleneck, and they had no buffer, they had no cache. There was no place that they could store data temporarily. Basically, the data had to be available at the same time as the CPU and vice versa. Systems were like that for quite a while. Basically, storage was the gating factor for performance. In the 70s, we started seeing external storage systems, and we started seeing cache. We started seeing RAM being used as a buffer. In the 80s and the 90s, for the first time, we started seeing cache on the storage array itself. And we started seeing plug-compatible storage where we had a variety of different options. You could say, do I want to buy storage from EMC or do I want to buy it from IBM? Nowadays, we've got a huge proliferation of storage products and a huge proliferation of connectivity options as well. I mean, I'm exaggerating here by saying, USB versus InfiniBand. You can't get much more different than that. But the point is, you can figure out, there's a whole bunch of different ways of connecting storage to your system, but really the storage is still pretty much the gating factor. We haven't yet gotten to the point where storage is faster than the system can handle. But we might get there soon, and I'd love to talk about that in a second. So when we look at a system, we have to decide what's the slowest link and how can we overcome that slow link. Is the slowest link the disk drive? Probably. But if we have cache in front of it, we have an intelligent controller in front of it, maybe we can mitigate that. Then where's the slowest link? Is the slowest link the network? Is it the network connectivity? Is it the bus inside the system? Is it the bridge between the system and the CPU? All throughout history of IT, we've been moving the point of contention, the bottleneck, back and forth, back and forth. And it's funny because there was a time when most systems, the bottleneck was actually right here. Effectively, the CPU was waiting, always waiting for the I/O boards. Now, thanks to PCI Express, we've got a scalable bus. We've moved that bottleneck away. I mean, but most systems basically are fast enough internally that you can pretty much do anything. Then the bottleneck became the network in many cases, because we were still looking at 1 gigabit Ethernet, 1 gigabit fiber channel, maybe 2 gigabit 4. Today, that bottleneck's going away. I was just talking to a guy who's doing advanced systems development. They're using 100 gigabit Ethernet as their connectivity between their nodes of their cluster. 100 gigabit Ethernet requires 16 lanes of PCI Express to support it. Most systems don't have that much more I/O. So basically you're using every or most of the PCI bandwidth in a server just to support a single network card. That's incredible. What goes on the back end of that? And that, then we start looking at the storage. We start saying, well, I mean, InfiniBand is 50 megabits, listen to me, 50 gigabits. Ethernet is already 10, fiber channel is 8, 16, maybe more. We have to start looking at the array once again and figuring out how we can eliminate bottlenecks on that side. So this is always evolving, and it will always be a problem. Now, there's one solution here that is pretty interesting to me, and that is cut out a lot of this stuff in the middle. Increasingly, as we've had faster and faster storage devices, and I don't mean disks, I mean flash in most cases, the way to use those things has been move that stuff closer and closer to the CPU. And that's, I think, a really interesting development in IT, because what it means is that we can maybe extract some of the theoretical performance from these flash systems. For example, If you want to see an example of this bottleneck problem in real life, look no further than the situation of the ultra performance all flash arrays. There's a bunch of companies out there that make storage arrays optimized for performance. In most cases, they're only delivering 8, 9, 10% of the theoretical performance of that system to the end host. Essentially, you're paying for millions of IOPS, and you end up getting hundreds of thousands of IOPS, which is still really good, but it's nowhere near what you're paying for. Look at most of these systems that use, high-end flash, PCI Express connected flash, and so on. You're only getting hundreds of thousands of IOPS. The reason for that is all this stuff in the middle. Once we start looking at flash and we start wanting to maximize that performance, what's going to happen is we're going to be starting moving that stuff into the server, moving that stuff closer and closer to the CPU. The ultimate that I've seen so far is what they're calling server class memory, or what I call, or server class memory, or storage class memory. I call tier 2 memory. Essentially, put memory, non-volatile storage as solid state right on the memory bus. Essentially put it right there. And that's kind of the ultimate way of getting rid of the bottlenecks. Then, once again, we can extract the maximum performance. The problem is that when we do all this stuff, we end up with not a storage system. We end up with a place to store data for one server, one application. This is not a solution either. What we need is intelligence. And the problem is there's very little intelligence in the system. So let's take a look at how data is stored. Do you love this crazy, crazy, crazy picture? So we humans communicate in letters most of the time, and images, and basically very high level ways. We write the Gettysburg Address. And the way that we think of things is as text, as files, as folders. And so computers historically have organized data the same way. You've got files, you've got folders, you've got file systems. But storage systems don't truly store data that way. Historically, traditionally, storage systems, block storage systems would take that and then go through buffer and go all the way down, and you'd end up with just blocks, just little bits of data all over your storage system. This is all well and good, and it works just fine until we talk about this idea of the I/O blender. Let me tell you what that means. Essentially, let's say that we want to maximize the use of flash and intelligence, and we want to sequentialize I/O and all that kind of good stuff that I just told you should do. That requires a really smart disk controller, and that disk controller has to know what it's doing. It has to have some information about what it's storing in order to do those things. It has to be able to say, this data should go together because it's going to be accessed together later. So if I want to sequentialize I/O, I need to have some concept of whether or not this data is related to each other or not. Because if I don't, if I just throw whatever random data sequentially on the disk, that helps me some in terms of putting it on the disk, but it helps me not in terms of getting it back off the disk later. If I want to be able to, to access that thing through a cache, well, that's not going to help me, because if it's totally unrelated, then it's totally unrelated, and I'm still going to slow down when I go to read it. So the problem with this stack is that at every point, each layer is simplifying what the layer below knows and the layer above knows, and each layer is translating it, and we're losing information. And so by the time it hits the disk, this is no longer the Gettysburg Address. This is now just bits, just some bits. And this is even worse in a virtualized world, because the hypervisor also does this. And so essentially, if you're trying to build a storage array to support hypervisors or to support virtualized hosts, you've just lost everything. So no matter how much intelligence, no matter how much CPU and compute power we have, we can't actually do anything with it. And so this is why the solution to this has to be some way to build a system that can demultiplex. So I like to call this the I/O blender. Essentially, you take your strawberries, you take your bananas, you throw them in the blender. You can't get your strawberries and your bananas back, no matter how hard you try. But if we could have a communications layer, if we could have some sort of alternate protocol that would allow us to send information along with those chunks of data, we might be able to get our bananas back. And that's what more advanced storage systems are trying to do. That's what VMware is trying to do, Microsoft. But that's also what object storage systems try to do. That's also what software-defined storage systems try to do. So if we're going to build a better storage, we're going to have to figure out a way to defeat all of these problems. We're going to have to figure out a way to embrace disks, not pretend that they don't exist, not pretend that we're going to get rid of them right away, but figure out a way to use them smartly, use them effectively. We're going to have to figure out a way to tier storage smart. We're going to have to attack the bottlenecks. But most importantly, I think, is we're going to have to get smart and we're going to have to integrate storage from application all the way down to the disk. And that's what I'm going to talk about in the next room right now. Seriously. This was me trying to be techie in 20 minutes. That will be me trying to take this up a level in a little more time. So I'm sorry that I don't have much time here with you guys. You may have questions. I don't care. We'll talk about it later, okay?